In this video, I'll show you how to solve the ALEKS problem called Understanding the Difference Between a Molecular and Empirical Formula. There are two versions of this problem, and I am going to solve both versions of the problem for you in this video. So in this version of the problem, we're given the structure of a molecule, and we're asked to write its molecular and empirical formula. In this notation, the letters are used to represent the atoms that make up the molecule. These lines represent the bonds that hold the atoms together. The dots represent random electrons in the molecule. All you need to pay attention to are the letters representing the atoms inside this formula. The molecular formula is the total number of each type of atom in the molecule. And so in order to come up with the molecular formula, we have to count up all of the atoms. This molecule has a total of 4 carbon atoms, so I'm just going to make a note of that, 4 carbons. Let's do the oxygens next. It has 1, 2, 3, 4 oxygens, and the hydrogens, it has 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. When we are writing the molecular formula for a molecule that is made up of carbons and hydrogens, and maybe oxygens are in there as well, there is a standard notation that we use where we write the carbons first, we write the hydrogens second in the formula, and we write the oxygens third or last. So by that I mean we're going to write the symbol for the carbon atom first, and we're going to follow it in subscript notation. We're going to follow that with the number of carbon atoms, C4. Then second, we're going to write the symbol for hydrogen, and we're going to follow that in subscript, the number of hydrogen atoms. And then last, we're going to write the symbol for oxygen, and in subscript notation, we're going to follow up with the number of oxygen. C4H8O4, that is the molecular formula for this particular molecule. Now, the empirical formula is different. The empirical formula is the lowest number ratio of all of the atoms in the molecule. So in this case, it's the lowest number ratio of carbon to hydrogen to oxygen. In the molecular formula, our ratio of carbon to hydrogen to oxygen is 4 to 8 to 4. When we're writing the empirical formula, we want to preserve this ratio, 4 to 8 to 4, but we want to reduce these numbers as much as possible. And basically, you're looking for the largest number that you could divide into each one of these numbers, still resulting in a whole number outcome. If you need to guess and check a few times to get this right, don't even worry about it, not a big deal. You could, let's say you could start by dividing all of these numbers by 2 and see what you get. If you divide everything by 2, I'm actually just going to write that down. Divide all these by 2, let's see what we get. 4 divided by 2 is 2, 8 divided by 2 is 4, 4 divided by 2 is 2. Can we get even smaller than that? Sure, we could divide all of these numbers by 2 as well. That gives us a ratio of 1 to 2 to 1. 2 divided by 2 is 1, 4 divided by 2 is 2. This ratio is the lowest number ratio of carbon to hydrogen to oxygen, and that is the empirical formula for this molecule. It is the lowest ratio of the atoms in the molecule. Sometimes the molecular formula and the empirical formula are exactly the same. So let's say, for example, what if we came up with a molecular formula that was CH5O3? I don't even know if that's real. I just made it up. This ratio of 1 to 5 to 3 is the smallest possible ratio of these numbers. I can't simplify this anymore. So in that case, the molecular formula and the empirical formula would be exactly the same. And like I said, sometimes that's going to be the case. You are not always going to be able to simplify the molecular formula down. Now let's look at the other version of this problem. In the other version of the problem, I've cut the instructions off. In the other version of the problem, you have 4 molecules, and it's asking you to sort these 4 molecules into groups in such a way that the groups all have the same empirical formula. So we want to put them into groups so that they have the same empirical formula. Now, this is going to be a bit of a tedious problem. In order for us to figure this out, we have to start by coming up with the molecular formula of each one of these molecules. And now you know how to do it. It's going to be pretty easy. We're going to do the carbons first. 1, 2, 3, 4, 5, C5. We're going to do the hydrogens second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to do the oxygens last. 1, 2, 3, 4, 5. C5H10O5. That is the molecular formula. Can we simplify it down to smaller numbers? Can we simplify and write an empirical formula? If we divide, we can divide 5 and 10 and 5. We can divide all of those by 5. So this would simplify down to an empirical formula of CH2O. That is our empirical formula, CH2O. And we're just going to designate that as group, I can't remember if it uses letters or numbers. Let's just say it's group 1. H2O, that is our group 1. Now we're going to go to our second molecule, and we're going to go through the same process again, writing the molecular formula. Let's count carbons first. 1, 2, 3, 4 carbons. Hydrogens will count second. 1, 2, 3, 4 hydrogens. And then oxygens will count last. 1, 2, 3, 4 oxygens. Can we simplify this to a different ratio of numbers? Yes. If we divide all of these numbers by 4, we can reduce this down to CHO, one of each. CHO is not the same as CH2O, so this is going to be in a new group. We'll call this one group 2. And we're going to carry on. Let's take a look at our next one. Same process. Start with the molecular formula. 1, 2, 3, 4 carbons. Hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And oxygens, we have 2. Can we reduce this down? Yes, we could divide all of these subscripts by 2, and that would give us an empirical formula of C2H4O. C2H4O, not the same as CHO, not the same as CH2O. So here we have a third. This is going to be group 3. This problem is not very exciting. Let's take a look at our last one last time. We have 1, 2, 3, 4 carbon atoms. We have 1, 2, 3, 4 oxygen atoms or hydrogen atoms, and we have 1, 2, 3, 4 oxygens. We can reduce this down to CHO if we divide all of these by 4. We have an empirical formula of CHO. Oh, finally we got a match. CHO, we have a match. We designated that CHO as belonging to group 2. That's how you solve this version of the problem.